Today I'd like to introduce you to metric conversions. We already studied the metric equivalent statements, and today I'd like to show you how to convert between metric units. So for example, you may have a problem that says convert 325 milligrams to grams. In order to do this conversion, you need a metric equivalent statement. Recall that 1 gram equals 1,000 milligrams. So this is called an equivalence statement. And from one equivalence statement, we can generate two conversion factors. A conversion factor is nothing more than a ratio or a fraction that relates the units to one another. For this one, we have 1 gram over 1,000 milligrams, or 1,000 milligrams over 1 gram. So both of these conversion factors can be used to interconvert between milligrams to grams or grams to milligrams. I want to introduce you to something called dimensional analysis. Dimensional analysis is a way to utilize conversion factors to cancel out the units you don't want and to keep the units you do want. Using dimensional analysis, you'll multiply the starting point, in this case, which is 325 milligrams, by one of these conversion factors that we have. You want the units that you want to convert to be in the numerator, and the units you want to cancel to be in the denominator. So I'm going to use 1 gram over 1,000 milligrams. Notice that if these are both written as fractions, milligrams are on opposite sides of the divisor, and therefore they are going to cancel out, and the only unit that I'm left with in the numerator is the unit that I want to get into, in this case grams. So we have 0.325 grams after we complete this calculations. Again, the milligrams have canceled out. Now you want to ask yourself a question. Does this make sense according to what you know between the gram and the milligram? Obviously, grams are the larger base unit and milligrams are the smaller unit. So if you go from a small unit to a large unit, as we did here, milligrams to grams, the magnitude of your number gets smaller. Let's try another example. Let's convert 9.0 times 10 to the negative 10 kilometers to, I don't know, nanometers. So in this case, perhaps I can't recognize the conversion factor that'll do it in one step. I can always generate equivalent statements that go back to the base unit. For example, I know that 1 kilometer is the bigger unit, is equal to 1,000 of the base unit, a meter. I also recall that the base unit, 1 meter, is equal to 1 times 10 to the 6th, or excuse me, 10 to the 9th nanometers. So I now have my two equivalent statements, and I can generate a total of 4 different conversion factors from each of them. 1 kilometer over 1,000 meters, or 1,000 meters over 1 kilometer. From the second conversion factor, I know that 1 meter is equivalent to 10 to the 9th nanometers, or 10 to the 9th nanometers is equivalent to 1 meter. So now I have all of my conversion factors that I need to convert 9.0 times 10 to the negative 10 kilometers. Using dimensional analysis, I'll start off with the 9.0 times 10 to the negative 10 kilometers. Any number is always considered to be written over 1. The first conversion factor that I need will get me out of kilometers and into meters. In this case, I'm going to use this conversion factor. I know there are 1,000 meters for every 1 kilometer. At this point, kilometers are going to cancel out, and I'll be in the units of meters. Resist the temptation to break this up into small problems because you'll introduce some sort of an error, typically a rounding error. Now, let me show you the next conversion factor. The next conversion factor that I'm going to use is going to get out of meters and into the smaller unit, nanometers. So I'm going to use this conversion factor because the units you want to put in the denominator are the units that are going to cancel. And the units that are left in the numerator, in this case nanometers, are going to remain. So I know that 10 to the 9th nanometers is equal to 1 meter. And note that since my units are on opposite sides of the divisor, they will both cancel. At this point, the only unit left in the numerator is the nanometers, and that will give us our answer. After you plug this into the calculator, I got 9.0 times 10 to the second nanometers. Now, you might ask yourself, why is it 9.0 times 10 to the second instead of just writing out 900? The problem is we would have ambiguous zeros. If you just wrote out 900, how can you show that that zero is significant? The only way to do it would be to write it into scientific notation. Remember that the conversion factors that we are using here and here, in terms of the rules for multiplication and division, have an infinite amount of sig figs and therefore cannot limit us. So we are limited to the 2 sig figs that we start off with. Both the 9 and the 0 are significant. So we have to show 2 sig figs in our answer, and the only way to do that with a number like 900 is to write it into scientific notation. Let's do one more example here where we convert from 27.7 microliters to deciliters. So in this case, I again want to write my conversion factors or my equivalent statements. I know the base unit, 1 liter, is equal to 10 deciliter, and 1 liter is equal to 10 to the 6th microliters. Now, another way to approach this would be to make one equivalent statement from both of these. I know that 10 deciliters now equals 10 to the 6th microliters because both of these equivalent statements give me this new equivalent statement. Now I can set up my conversion factors using dimensional analysis, starting off with the 27.7 microliters. Assume that's written over 1. Multiply that by a conversion factor that I generate from this equivalent statement. I want to get out of microliters, so the 10 to the 6th microliters will be in the denominator, and the 10 deciliters will be in the numerator. Again, the microliters are going to cancel. And after you do the multiplication across the numerator, we're obviously going to get 277, and divide that by the 10 to the 6th, I got 2.77 times 10 to the negative 4 deciliter. Don't forget to indicate the units. Now you want to ask yourself a question. In this problem, we went from microliters, a small unit, to deciliters, a larger unit. When you go from small to large, the magnitude of your number should get smaller. Did it? It certainly did.